Okay. In the previous lecture, we talked about row space and column space. We just took their definitions, and we now have basis for matrices. To find a base of a matrix, what we do all depends on reduced row echelon form. Okay? You need to reduce the matrix to echelon form. We apply the row operation to get the reduced row echelon form of the matrix. We say let A be a matrix M by N. A is a matrix of M by N. So here we have M rows and N columns. And matrix E is in row echelon form of A. Matrix E is the matrix that we get by reducing matrix A to reduce row echelon form. Okay? If we change A to the form of reduced row echelon form, we get a matrix. That matrix is E. Then the row vectors with the leading ones, all those rows, and which include the leading term 1, the set of those rows is called basis for the row space of A. It's called basis for the row space of A. Look at this example. Here we have given A. A is this matrix. We first change the matrix to reduce row echelon form. How? This is 1. We try to change these to 0. Okay? We change these to 0. And then we come to here. We try to change this to 0. Then here, we try to change this to 0, this, and so on. Okay? Good. Like that. After converting the matrix to reduced row echelon form, we get this matrix. We get this matrix. So you should know how to reduce a matrix to reduced row echelon form. Okay? Here, this is matrix E. E is obtained from A by applying the elementary row operations, and this is the reduced row echelon form of matrix A. What we do here, we say the row basis, look, the basis for the row space A, the basis for matrix A, we choose it from here. We choose it from here. Which of these rows, here we have 1, 2, 3, 4. We have 4 rows here. Which of these rows is the row space of A, of matrix A? What we do? We just choose those rows which starts with 1. Look, this row, does it start with 1? Yeah, I mean the first non-zero element is 1. This one, look, the first non-zero element is 1. We choose that also. We choose row 2 also. And row 3. Yes, we choose this also. That means here we have 3 rows or 3 vectors. Okay? So the base for the row space A is this row, and this row. It's these 3 rows, R1, R2, and R3. So the row space is these 3 vectors. As you see, we just took these 3, this, and this. Okay? So it's important to know how to change a matrix to reduce row echelon form. We talked about this before in chapter 2. Okay? After reducing it to this form, look, we just choose those rows in which the first non-zero element is 1 in it. We have these 3 rows. So we write down this row, and this row. These 3 rows are the row space of matrix A. It is the basis for the row space of matrix. Then we have basis for column space. We have basis for column space. We do the same. We do the same. But here, what we do, let me explain on this example. After changing the matrix to reduced Rotation form, what we choose to be a basis for the column space. We choose those columns, look, those columns which include the first non-zero entry in these rows, okay? Which one? We just choose those columns. Look, before we choose the columns, what we do? We just select the first non-zero entries of the rows, which is 1, okay? This one and this one. Look, this one is in this column. So this column, and this column, these 3 columns are basis for the column space. Not these 3 columns. We don't choose these 3 columns here. We choose this one, which is the corresponding columns in matrix A. So it's column 1. We choose column 1 in matrix A. It's column 3. We choose column 3 matrix in matrix A. This is 5. We choose column 5 in matrix A. These 3 columns are the basis for the column space. That's the difference between row space, basis for the row space and column space. For the row space, we choose from this. We choose from matrix E. But for the column space, we return to the original matrix. We choose those corresponding columns. Okay? Look at this. This one, it's matrix A. In matrix A, what we do, we apply the elementary row operation to get this matrix. In this matrix, look at the leading entries. Leading entries, which is 1. Only those leading entries, which is 1. Here, we have this leading entry. And here, we have this leading entry. And here, we have this leading entry. Look, these leading entries are in columns 1, 3, and 5. We return to matrix A. We choose those 3 columns. We choose those 3 columns in matrix A. Here, we choose columns 1, 3, and 5. These 3 columns, this one, and this one. These 3 columns together called the basis for the column space A. That's it. These are the basis for the column space. We choose these, okay? We don't choose it from here. We don't choose these columns. We return to the original matrix. We choose from there. Based on this, look here, we choose these 3, columns 1, 3, and 5. Okay? That's it. It's row basis for the row space and column space. Then we have dimension and rank. Dimension of a row space of A, it is the number of non-zero rows in the echelon form of A, or it is the number of bases for the row space. In the above example, how many bases do you have here? 3. It's 3 rows. So the number of these bases, it's called dimension or rank. Rank of A. Sorry? Choose the rows that ends with 1. Separated and yes. It's just the basis. Okay? It's for the basis. We just choose those 3. and we name them R1, R2, R3, A1, A2, A3, and anything like that. Okay. Here, how many bases do you have here? 3. That means dimension is 3. Or rank is 3. Dimension and rank are the same. So both are the same. So dimension and rank are the number of bases that you found. Okay? And dimension of the column space A, it's the same. It's the number of bases for column space. Look at the second example. Here, dimension for this column space, is columns 1, 3, and we have 3 bases. So the dimension is the number of bases. How many bases do you have? 3. So it's 3. Dimension is 3. And also rank is 3. Rank is, sorry. For rank, it is the submatrices of the given matrix in which it is determined is not zero. Look, if you find, look, 1, 2, 3, 4, 5, 6. It is 6 by 4. It is 6 by 4. We cannot find a determinant of a 6 by 4 matrices. What we do, we pick a 4 by 4 matrix from this matrix. Let's pick this 4 by 4 matrix. The determinant of this matrix is 0. Determinant of this matrix is 0. What we do, we reduce it. Then we reduce a row and a column. Let's choose this submatrix. So it's not 3 by 3. It's not, sorry. Here, as I said, we took these 4. Okay. If we pick this submatrix, it is 3 by 3. Its determinant is not 0. So the rank, it is the size of the matrices, of the submatrices in which the determinant is not 0. The determinant of this is not 0. Even if we take any 3 by 3 matrix from it, it's not 0. May someone else take this 3 by 3 matrix. Even this one, its determinant is not 0. But if we pick any 4 by 4 matrix from this, we get 0. The determinant is 0. Okay? That means here, it's the rank. Okay? The rank is also the number of bases. It's the dimension. It says determine the rank and basis of the row space of the matrix. Look, for this matrix, what we find the rank and the basis of the row space. What we do first for finding rank and row space, we need to apply the elementary row operation, okay, to reduce the matrix to the form of reduced row echelon form. Okay, what we do, we change the matrix to reduced row echelon form. That's it. And this matrix, how many non-zero rows do we have? 2. So these two rows become bases. Let's say it's R1, R2. These two are bases for the row column. Okay, and what's the dimension? How many bases do you have here? 2. We have R1 and R2. So it's dimension 2. Or the rank is also 2. The rank is also 2. What if it's asking about the basis for the column space? Look, we have leading entries here in these 2 positions. Okay, it's in the first column and in the second column. So what are the bases for the column space? We are returning to matrix A. What do we choose here? We choose columns 1 and 2. So this column and this column are the basis for the column space. Okay? These two are bases for the column space. But for the row space, we directly choose it from here. We just choose the non-zero rows. That's it. Here we have another example. It says, let A be this matrix. Find basis for the row space of matrix, basis for the column space of matrix, and also rank A or dimension A. These two are equal. Okay? What we do first, for finding basis for either row space or column space, we need to change the matrix to reduce row echelon form. How? From this one, we try to change these two to 0. And then from this one, we try to change this to 0 and so on. Okay? Look. This is the reduced row echelon form of the matrix. What are the basis for the row space? How many non-zero rows do we have? We have this and this. Okay, so this vector and this vector are the basis for the row space. 1, -1, 3, and -2. This one is, and also 0, 0, 1, -3/4. These two are basis for the row space. Okay, so what are the basis for the column space? We first select the leading term, which are 1. Okay, we just choose these leading terms. Then the position here is in row 1, and this is in row 3. What we do, we return to the given matrix. Okay, we choose rows 1 and 3. Let's return to matrix A. Sorry, we choose columns 1 and 3, not row. We choose columns 1 and 3. This is 1 to -1, and also 3 to 5. These two are basis for the column space. Basis for the column space. So here, that's it. These two are basis for the column space. So what's the rank of the matrix? It's 2. Okay, be careful here. You must get the same number of bases for the row space and for the column space. Okay, the same number of bases for row space and column space. As you see here, we got 2 for both. In the previous ones, we got the same. Then we have basis for the vector space. Rank is the number of these vectors. How many vectors? How many bases do we have? 2. So rank is 2. And also dimension is 2. Okay, dimension and rank are the same. And even here, how many bases do we have here? 2. So the rank is 2. Okay. Then we have basis for vector space. What if we have a vector space? How to find the basis for it? It's similar to the previous one. We write down the vectors in a matrix form. Then we do the same. Look, it says suppose given a vector space V is spanned by the set of these vectors. Okay, this is up to x vn. Okay, if V is a vector space, V is a vector space. It says it is spanned by the set of these vectors. Okay? Then we say we write down the matrix form of the given vectors. We have given V1, V2, V3, and so on. We write down V1 as the first row. Okay? V2 as the second row, and so on. We write down the given vectors in the form of a matrix. That's it. This is V1, this is V2, up to Vm. Then, basis for the row space of the given vector space, we need to first change this to reduce row echelon form, and we do the same as we did before. The number of those, the bases are the non-zero rows. Okay. Look. Here, the vector space V is the row space of A. Here, dimension V equals to the dimension of row space of A, also equals to rank of A. It's the same as above. It says the dimension here for this vector space is the same as what we did before for the row space. Then basis is the same. Base is the number of, is the set of all non-zero rows. Look at this example. It says, find the dimension and a set of bases for row space vectors for the vector space V spanned by these three vectors. It says, find the dimension and basis for V. Okay? For the row space of vectors, these four vectors. Here, what we do, we need to first write down these four vectors in a matrix. As it says, for a row vector, for a row space, that means V1 is row 1, V2 is row 2, V3 is row 3, and so on. Okay? If you write down this, in a matrix form, it is 1, 2, 0, 2, 5. Then -2, -5, 1, -1, -8. 0, -3, 3, 4, 1. Then we have 3, 6, 0, -7, 2. That's the matrix form of the given vectors. If it says it's column space, so if it says it is row space, then we work on this matrix. We find the base and rank for this matrix, which will be the same as the base and rank for the vector space V. Okay, it's asking about finding the rank and basis for vector space V. What we do, we write down the vectors which span V in a matrix, and we find the basis and rank for that matrix. And we already studied this, how to find the basis and rank for row space of a matrix. Look, we first change the matrix to reduce row echelon form. We get this. Okay? Then, what we do? Here, the number of non-zero rows, we have 3. These 3 vectors, these 3 rows is the basis for the matrix. Okay? These 3 rows, this row, and this row. We write down, let's say R1, R2, R3. These 3 are called the basis for the row space A, which is the basis for the row space of the vector space V. Okay, so the bases are these 3. And what's the rank? How many bases do we have? 3. So the rank is 3. And also the dimension is 3. That's it. It's easy. Then basis for column space, it's the same. But here, arranging the rows and columns is different from the above one. Here, we say suppose given a vector space V spanned by a set of column vectors. It says spanned by these column vectors. That means the first vector is column 1 in the matrix. In the previous one, we said V1 is row 1, V2 is row 2, and so on. But if it says in column space, column vectors, here V1 is column 1, V2 is column 2, V3 is column 3, and so on. That's only the difference from the above one. Here's the same as we did above. It says find the dimension and a set of basis vectors for the vector space V spanned by. Look, the vectors are given as columns. Even if it doesn't say it's column space or column vectors, you should know that these are columns. So if we have given V1 is 1, 0, 1. It's like this, and we have all in the horizontally, but we have capital T on it. This means transpose. So transpose change row to column. Okay, change row to column. So this is a column. It's not a row because we have transpose of it. Now we have 1, 2, 3, 4, 5. We have 5 column vectors. We have 5 column vectors. We arrange them all in a matrix. We get this. This is V1, this is V2, up to this V5. These are the arrangement. This is the arrangement of the given vectors. Now, we apply the elementary row operation to get the reduced row echelon form of this matrix, and we get this. Okay. Now, what are the basis of the column space? What are the basis of the column space? For basis of the column space, we just select the leading entries. Okay. This is a leading entry. This is a leading entry, and this is a leading entry. This is in column 1. This is in column 2. This is in column 4. That means columns 1, 2, and 4 in the given matrix, the original one. In A, we choose columns 1, 2, and 4. So this column, and this column, these 3 together are basis for the vector space. And also, the rank is what? It's 3. How about the dimension? It's also 3. Okay, these 3 columns are the column, the basis for the column space. These are those, and also the dimension is 3. Then we have nullity. Say nullity of matrix A defined as dimension of the null space of A. So we first need to find the null space. The dimension of the null space is called nullity. This is dimension of N of A. N of A means null space of A, of matrix A. Look at this. Let's see how to find the null space. We need to first find the null space. Then for nullity is the dimension of the null space. It says find a basis for the null space of this. This is the null space. It says this is a null space. How to know how to show that, how to find the null space here. We say a null space is a space in which the image of it is 0. The image is always 0. Here we say we need to first write down this. Look, as it says, this is a null space. That means this equals to 0, equals to 0, equals to 0, equals to 0. What are these? We have two, let's say x1, x2, x3, x4, x5. And for this one, we have 5x. 4, we get a system of linear equations, includes x1 to x5. Okay, and all the right hand sides are 0 because it's just it's a null space. We equal to 0. That's it. This is our system. Now we solve this system by using either Gauss elimination or Gauss sort. We need to find the values of x. Okay. What we do, let's use Gauss elimination. Here we get this matrix. This is the right hand side. This column is the right hand side. It's all 0. And these are the reduced row echelon form of the augmented matrix of this system. The augmented matrix is this. If we just add a column here, this matrix is the augmented matrix of this system. Okay? Then we solve it. We apply the elementary row operations to get the reduced row echelon form. That's it. Now, how many equations do you have which is not 0? Not all 0. 1, 2, 3. And how many variables do you have? You have x1 to x5. Okay? What's the difference between them? Look, the number of equations is less than the number of variables by 2. Okay? That's 3 and that's 2. That's 5, sorry. It's 3 and 5. So now we just select the leading variables. 1, this, and this. Look, we go through the rows. The first non-zero entry are leading entries. We choose them. This is coefficient of x1. This is coefficient of x3, is it? The first column elements are all coefficients of x1. The second are x2, and then x3. How about this one? x4. So these are not free variables. These are leading variables. We have two free variables. What are they? x2 and x5. We name each of them. Let's name S, sorry, x2 to be S, x5 to be T. Okay? Now, let's first write down these equations. From this row, we get 1x4 equals to the right-hand side, which is 0. So x4 is 0. Let's write down. x4 is 0. x2 is S. x5 is T. Then, from these, we can find the values of x1 and x3. How about x3? Where do we have x3? We have it in the second row. Okay? x3 plus x5 equals 0. So what's x5? Here, let's write down the equation first. So x3 plus x5 equals 0. x3, what's x5? Is t. So x3 is negative t. x3 is minus t. We now have x2, 3, 4, and 5. We just need to find the value of x1. We can get it from the first equation. Let's write down the equation in the first row. It's x1 plus x2. Coefficient of x3 is 0. Coefficient of x4 is 0. We don't need to write down these two terms. Coefficient of x5 is 1, so plus x5 is equal to 0. Now, we already found these two. We just replace them here. X5 is t, and x2 is s. So x1 is, plus s plus t equals 0. So x1 is minus s plus t. x1 is minus s plus t. Now, we write down this as a column vector, okay? Let's write down them as a column vector. But in order, first x1, then x2, and then up to x5. Let me delete this one. Here, we have x1 is minus s minus t, is it? x2 is s. x3 is negative t. x4 is 0. x5 is t. We can write down this as a sum of two matrices. One as a sum of two column vectors. One includes t terms, one includes s terms. Okay? Can we say this equals to minus s plus minus t? Can I say that? Yeah. For the first entry, it's minus s minus t. Can I say it's minus s plus minus t? Yes. And in the second one, it's s and 0. S plus 0 is s. Then for negative t, 0 minus t. We separate them. We put all t terms together and all s terms together. It's 0. So both are 0. Okay? And t, 0, t. That's, we have these two matrices. If we take s as the common here, what we get? If we take s, here we get minus 1. Here we get 1. So we take s as the common. If we enter s to that vector, we get minus s, 0, 0, 0. And even here, if we take t as the common, what we get? It's minus 1. This is minus 1. And this is 1. I will write down t here. So these two vectors that we got are the bases. That's it. These two are bases of what? For the null space. These two are bases for the null space. As you see, how many bases do you have? 2. So the nullity is 2. The nullity is 2. That's all. That's this V1 and V2. It's those two vectors without S and T. And the nullity is the number of bases, which is 2. Then here we say rank of a matrix plus nullity of the matrix is equal to n. Is equal to n. Okay? Okay. We say if A is a matrix with n columns, if we have n columns in matrix A, then rank A is plus nullity of A is n. Okay? It is n. N is the number of columns in the given vector. as you see, rank A, we find as the non-zero rows in the reduced solution form of A. Okay, or for the column 1, we just pick the leading entries in the reduced solution form, and then we choose those columns in the given matrix. Okay, rank A plus nullity of A is n. What's the rank A? Rank A is the number of leading variables. Okay, it is the number of leading variables. Rank A is the number of bases for the column space. And nullity is the number of free variables. It is the number of free variables. Look, rank A is the number of, here, look at this. How many? What are the leading variables? X1, X3, and X4. These are leading variables. So what's the rank of A here? We choose this column, and this column. Where? In the given matrix. We choose these three, which are the basis for the column space. Okay? So what's the rank of the matrix? Is the number of column space. How many column spaces do you have? So basis for the column space, we have 3, X1, X3, and X4. Or you can say it's the number of leading variables. So what's the rank of nullity of the null space? Or what's the nullity? Nullity is the rank of the null space. We say the rank of the column space plus the rank of the null space. These two together is the number of columns. How many columns do we have here? Up to here, not this. It's the right-hand side. Okay? 1, 2, 3, 4, 5. Okay? We have three leading variables. And how many free variables? We said we have 2 free variables, X2 and X5. That means how many free variables do you have? 2. So the rank of the null space or the nullity is 2. So the sum of these two, it was 3. The null space, base for the null space is, rank of the column space. Rank of the column space is 3. And rank of the null space is 2. The sum of these two is 5. So how many variables do you have here? 5. You have 5 columns. So the number of columns is the number of leading variables plus the number of free variables. So it's the end of this chapter. Let's take a break for 10 minutes. Okay, we now have a new chapter, which is linear transformation. Here we have the definition of a mapping. We say, define that a mapping T from vector space V to another vector space W. Here we talk about those functions which is from a vector space to another vector space. We name it by T. We say T is from vector space V to the vector space W. Okay? We say V is called domain. V is called domain. And W is called codomain. Okay? Codomain of the function. Of course, the function is T. We say if T to be a function from V to W, V is domain and W is codomain. Here, T of V is W, is equal to W. We say if T of V is equal to W, that means if let me explain it in a diagram. If we have T from V to W, let's say we have V1, V2, V3, V4. If we have 4 vectors in it, and if we have, let's say W1, W2, W3, okay? We say if T of V1 to be W1, T of V2 to be W2, T of V3 to be W3, T of V4 to be W3. Look, here, as you see, we have no any more vectors here, and which doesn't get an arrow from vectors of V. That means W is called range of T. It's called range, okay? But here, V is domain and W is codomain. When do we say codomain equals to the range? If T of V equals W, in that case, we say codomain is range. If you have W4 here, but we have no any arrow from vectors of V to W4. In this case, we cannot say W is range. The range is only these 3 elements. The range is only those 3 elements, okay? But if these 2 are equal, that means if we have like this, we say W is range. The vectors in W called the range of T. The set of all image vectors in W called the range of T, and the set of all V in V such that T of V equals W. If T of V equals W, called pre-image of W. Here, the pre-image of W1 is V1. Pre-image of W2 is V2. Pre-image of W3 is what? It is V3 and V4. Okay? It's V3 and V4. It is these concepts. You have domain, codomain, range, and pre-image. You have these 4 concepts here. In this example, it says, define a mapping T from R2 to R2. It's defined by this formula. T of xy is equal to x plus y and x minus y. It's defined by this. If we have 2 elements in vectors in the domain, we say their image is the sum of the elements and the difference of the elements. Okay? It says find the image of the coordinate vectors E1 and E2 and the mapping T. We find these 2. We find T of E1 and also T of E2. How to find them? Let's find them here. T of E1 is T of 1 and 0 is equal to what? Look, based on this definition, it is first plus second, 1 plus 0, and first minus second. First is 1, second is 0, 1 minus 0, as you see, first minus 0 here. And this equals to 1, 1. This is the image of E1. This is the image of V1. We just use the definition for finding the image of any vector. For the second one is T of E2 is 0, 1. It is 0 and 1. This equals to what? We apply the same definition. First plus second, which is 0 plus 1. Then, in the second entry here, we have first minus second. Okay? First, 0 minus 1. This is first. This is second. As you see, x minus y. Above 1 minus below 1. It's 1 minus 0 minus 1. And it is the sum of 0 and 1 is 1. The difference of 0 and negative 1 is negative 1. That's it. Okay? This is the image of E2. It's how to use this definition for finding those two images. It's easy. Here we have another example. It says for any vector v1, v2 in R2, let T from R2 to R2 defined by this. T of v1, v2 is equal to v1 minus v2. Look, second later, شمال هي v1 v2 يكم دوم. اوكي انا شي اكاتت شي يكم ناقص دوم انجا يكم زائد دو ضربي دوم اتري يكم دوم هر جماري يكن اما مثلا جبت شي. Okay, look, it says find the image of this. So T of negative 1 and 2 is يكم زائد يكم ناقص دوم. في ام بيناسه جاكوتي يكم اكاتي يكم ناقص دوم minus 1 minus 2 جاكوتي دوم تشيا يكم زائد دو ضربي دوم. The first one is negative 1 plus 2 times the second. This is 1 يكم امش دوم ويا يكم زائد دو ضربي دوم دو كرة دو شركات شو. Now we simplify this. This equals to minus 1 minus 2 is minus 3. Negative 1 plus 4 is 3. So this is the image of this vector. Okay, we do the same for any other vector. We just use the definition. As you see, in the previous one, we use another definition. The definition should be given in the question. That's it. Then it says, find the pre-image of W to be negative 1 and 11. It's different from the above one. Here it's asking about pre-image. It's asking about pre-image. That means T of, let's say V1, V2 is equal to negative 1 and 11. What's T of V1, V2? We need to find V1 and V2 here. We need to find V1 and V2. What we do here, T of V1, V2, based on the definition, it is V1 minus V2. Then V1 plus 2 V2. This equals to what? Equals to negative 1 and 11. Here we have 2 elements, and in the other side we have 2 elements. That means V1 minus V2 equals negative 1. And V1 plus 2 V2 equals 11. Here we get 2 equations. We solve these 2 equations to get the values of V1 and V2. Let's do it. Here we have V1 minus V2 equals negative 1. And V1 minus 2V2 equals 11. Okay, you can use any method for solving this system. It's a system of 2 variables, of 2 equations. You can use elimination, you can use substitution, you can use any method. Okay, here if you multiply the first one by 2, we get 2 2, it becomes minus 2. Now we add these two equations. These two are cancelled. Sorry. It's plus. Yeah. You multiply it by 2. These two are cancelled out. Negative 2v2 and 2v2. When we add them, you get 0. And here we get 2v1 plus v1 is 3v1 equals negative 2 plus 11 is 9. So v1 is 9. This is v1. We plug this into any of these equations to get v1. Sorry, it's 3, not 9. Sorry. Yeah. Thanks. It's 3. Then we plug v1 into any of the two equations. Let's. Sorry? Yes, you get the same result. You must get the same result in both. If you plug it into the first equation or in the second equation. Let's plug it into the second equation. We get v1 is 3. So you get 3 plus 2v2 is 11. We move this to the other side. We get minus 3. 11 minus 3 is 8. So we get 2v2 is 8. How about v2? Is 4. That means we get 3 and 4. So the pre-image of negative 1 and 11 is 3 and 4. That's how to find the pre-image. For the pre-image, we need to find the values of v1 and v2. Or if we have a vector in v3, in R3, we say we need to find v1, v2, v3 based on the definition. Okay? That's it. Then we have definition of linear transformation here. We say a mapping T between vector spaces V and W that satisfy the two properties is called linear transformation from V to W. This is the definition of linear transformation. We say if we pick any two vectors from the domain, from V, if we find the sum of them first, then we find their image. It must be equal to the sum of their images. So T of U plus V must equal to T of U plus T of V. Okay? Here we find the sum in V first, then we find its image. But here we find their images, then we find the sum of them in W. Okay? That's it. And even if we multiply a scalar by any vector in the domain, we must get that the scalar multiplied by the image of the vector. Okay? T of Cu must equal to C times T of U. If any function satisfies these two conditions, is called linear transformation. It's called linear transformation. We take some examples about that. It says show that this function is a linear transformation from R2 to R2. So you must show that this definition satisfies the above conditions. We say we must show that T of UV or VU must equal to T of U plus T of V. What's U and V? In each of them, we have two entries because it says from R2 to R2. So if we pick any vector, the vectors are in the form U1, U1, U2, or V1, V2, or A1, A2. We have two elements in it. Okay? So let's show that these two are equal. Let's first find this. T of U plus V, sorry, not V. U plus V. We say let U to be U1, U2. and V to B, V1, V2. We have, we pick these two vectors in V, in the domain. Let's first find the sum of them. What's the sum of U plus V? It's two vectors. We just add the corresponding entries. It's U1 plus V1, comma, U2 plus V2. It's the sum of U and V. This is the sum of U and V. Then, let's find both sides, this and this side. They must be equal. Okay? What's T of U? What is T of U? It's T of U1, U2. It is U1 minus U2, comma, U1 plus 2U2. Is it? It is U1 minus U2. Sorry. Comma. U1 plus 2U2. This is T of U1, U2. How about T of V1, V2? It's the same. It is V1 minus V2, V1 plus 2, V2. Okay, then let's find the sum of these two. Okay, because in the right hand side you have the sum of these two functions. Okay, the sum of these two is U1 U1 minus U2 plus V1 minus V2. Okay, we just add the corresponding elements. We add this with this one. We say T of U plus T of V is equal to U1 minus U2 plus V1 minus V2. Okay? And if you rearrange it, it is U1 plus V2 minus U1. It is U1 plus V1 minus U2 plus V2. It's the same. Then, comma, adding these two, adding those two entries, it is U1 plus V1 plus 2 U2 plus V2. This is the sum of T of U and T of V. We get this. That's it. Okay. Now, let's find T of U plus V. How to find this? We just look. We just think that this is the first entry and this the second entry. Let me write down again. We said U plus V is U plus V is U1 plus V1, U2 plus V2. أما جاكوتيك وجاكوتيك. If you apply the definition on that vector, what we say? This first minus second. Look, the definition says this. This is our definition. It says first minus second, then comma, first plus 2 times second. Okay? It's first plus 2 times second. So T of U plus V is T of this. And it's equals to first minus second, is it? It's first U1 plus V1 minus second is U2 plus V2. Then comma. And then first plus 2 times second. First is U1 plus V1 plus 2 times second. Second is U2 plus V2 is equal to T of U plus T of V or not? What's T of U plus T of V? That's it. These are equal. Is it? So you get the same. It satisfies the first condition. How about the second condition? For the second condition, it's the same, but here we just take one vector. If we take a vector, let u to be u1, u2, then we need to show that t of c times u must equal to c times t of u. It's easy to show this. We just apply the definition in both. You get the same. We get the same. Look, that's it. It's the first and the second. We need to show that t of cu equals c t of u. Okay, we get this. And if we take this as the common, this is t of u. So you get c t of u. It's easy to show this. It's for yourselves. So we show that this function, we showed that this function is a linear transformation because we could satisfy both conditions. We could satisfy both conditions for this function. And so the function is a linear transformation. Then we can change the definition of linear transformation to this. We say let V and W be vector spaces. We say the mapping T from V to W is called a linear transformation if and only if. Just satisfy this condition. If it satisfies this condition, means it is the linear transformation. Okay? Instead of using the above two conditions, we just use this here. We say a mapping is called a linear transformation if it satisfies this condition. This is the condition. If you multiply u by c, then adding to v and mapping it, it must equal to c times t of u plus t of v. If these two are equal, we say the mapping is a linear transformation. Look at this. It says, let A be an m by n matrix. In matrices, look, here A is a matrix. It's a matrix of m by n. Define a mapping T from Rn to Rm. T of x equals A times x. That means if we take any vector, we say it is A times the vector. Okay? Let's take T of, and let's say V. It equals to what? Equals to A times V. A is the given matrix, is a given matrix, okay? So how about T of U plus V? It equals to A times U plus V, okay? We always multiply matrix A to this vector here, okay? This is the definition of the mapping. It says, show that T is a linear transformation. What should we show? We need to show that T of C times U plus V must equal to C times T of U plus T of V. Okay, what's this? This equals to A times, this equals to A times CU plus V. How about the right-hand side? In the right-hand side, this equals to C times AU plus AV. Between these two, what's common? What's the common? A. If we take A, what we get? We get CU plus V. Is this equal to the above one or not? Yeah. So we showed that both sides are equal. And it satisfies the condition of linear transformation. So the mapping is a linear transformation. Let's answer for the first part. And then it says, let A be this matrix. We use the above definition here, this one. Find the image of this vector and this vector. How to find the image of these vectors? We just multiply A by these vectors. That's all. We just multiply A by these vectors. What's T of this? T of 1, 1, 1 is A times 1, 1, 1. What's A? A is the given matrix. We just multiply these two. How about T of this? It's the matrix multiplying by the vector. It's done here. T of this is the matrix times the vector. We multiply these two, we get 2 and 4. Shall we do the multiplication or it's easy? Here we multiply this row by this column and we put it in the first entry. Here it is 1, 2, negative 1. 1 times 1 plus 2 times 1 plus negative 1 times 1. It is 2. It's 3 minus 1 is 2. Then we pick this row. Negative 1, 3, and 2. Negative 1 times 1 plus 3 times 1 plus 2 times 1. It is 4. So this is the image of this vector. Okay. How about this vector? It's the same, but here we get 0, 0. In both entries, we get 0. So these are the images of these two vectors. We just use the definition. The definition should be given, then you can find the image of a vector. Okay. It's easy. Linear transformation is easier than the previous chapter, actually. Here, we have some examples in calculus which are not linear transformations. For example, sine x. Sine x is not a linear transformation because sine of x1 plus x2 doesn't equal to sine x1 plus sine x2. Okay, if x1 and x2 are vector u and v, let's say, it doesn't equal to sine u plus sine v. We cannot separate it in sine function. And even x squared is not a linear transformation. It's not a linear transformation. Because if we pick x1 and x2, so we say f of x1, x2 must equal to f of x1 plus f of x2. But here it doesn't equal. x1, x2, its image is x1 plus x2 squared. But f of x1 is x squared. F of x2 is x2 squared. Okay? Based on this definition. These two are not equal. These two are not equal. And even this one is not a linear transformation. That's it. Okay? Here's some examples in calculus which are not linear transformations because they don't satisfy the conditions of linear transformation. Here, we say if here we have two type of transformations: zero transformation and identity transformation. Zero transformation is a transformation in which the image of all vectors is 0. The image of all vectors is a 0 vector. Then we say that transformation is a 0 transformation. Okay? But if the image of every vector is the vector itself, it is an identity transformation because we get the same. We always get the same. In this case, this one is. Here, we say 0 transformation is a transformation which the image of all vectors is 0. But identity transformation is a transformation which the image of every vector is the vector itself. Here we have these properties of linear transformation. We say a function is a linear transformation if it satisfies these conditions also. it must satisfy these properties. So all the linear transformations must have these four properties. T of zero vector must zero. Okay? So the image of any zero vector must be zero. Must be zero. That's the first property. Then T of negative V must equal to minus T of V. It's like the scalar. T of U minus V is equal to T of U minus T of V. And if V to be the linear combination of V1 up to Vn, then T of V is the image of all terms. It's easy. Here, if we have given a function, if it says it's a linear transformation, it must satisfy these properties also. So if a mapping doesn't satisfy at least one of these, we say it's not a linear transformation. Okay? All the linear transformations must satisfy these four properties. Here we have a mapping from R2 to R2 by this. That's the definition. T of xy is exponential of x and exponential of y. Okay? This is the definition. It says, determine whether T is a linear transformation or not. What we do, we just, you can use the conditions of transformation, and also you can use the properties. If it doesn't satisfy at least one of them, we say it's not a linear transformation. We say, in the properties you have that T of 0 must equal to 0. That means if we pick a zero vector, we must get zero vector. That so here T of 0, 0 must equal to 0, 0. Let's see if this equals or not. What's T of 0, 0 here? It's equal to what? It is e to the power 0 and e to the power 0. What's e to the power 0? It's 1. Okay? It's 1, 1. So it doesn't equal to 0. It doesn't equal to a zero vector. That means this mapping doesn't satisfy that condition. So it's not a linear transformation. That's enough. Okay? It's not a linear transformation. And also you can use any other property. Example 7, it says define a mapping T from Mn, a matrix, it's a matrix. M is a matrix. From a matrix M by N to a matrix of N by M by this. This is the definition. It's AT means transpose of A. We change the first row to the first column, the second row to the second column, the third row to the third column. Have you studied this? متى نحن ندو transpose matrix؟ الهاي سكول جد نحن ندو؟ Okay, look, let A to be 1, 3, 2, 2, 1, 0. What's AT? AT means transpose of A. We change the first row to the first column. Okay. 1, 3, 2, yeah. 2, 1, 0. That's the transpose of A. Now, it says, is this function is a linear transformation or not? Yes. شو تمترني؟ كيف؟ Here we have a mapping from a matrix M by N to another matrix N by M, was defined by this. T of A is a transpose. So if we give any matrix to the function, it gives us the outcome is its transpose. Okay, so the vectors here are matrices. The vectors here are matrices. Okay, and the outcome is also a matrix, but it is the transpose of the input. Then it says show that the mapping is a linear transformation. As it says show that, so it must be a linear transformation. But if it says determine whether it is a linear transformation or not, so it may be or not. Okay, but as it says show that, so it's true. You must show that it's a linear transformation. How to show this? Here, look, it satisfies both conditions here. You can either use this OI, or you can use, look, let me explain this, then I'm gonna give you another way for doing it, because in the previous slides, we said that we have only one condition. You can apply only that condition to show a function is, a mapping is a linear transformation or not. Yeah. B is a matrix, it's a vector. You know, in the previous ones, we took U and V. And here we take N. It's a vector. Okay? It's a vector in the domain. Here, it says the mapping of the sum of vectors is equal to what? T of A plus B. If we give anything to the function, if we give anything to this, it gives us its transformation. Even if we have 10 vectors, it gives us the transform of all vectors. Okay? Here, the vectors here are matrices. We have A and B, the sum of these two. You can use either these two ways for showing that a function is a linear transformation or not. If T of, let's say, U plus V is equal to T of U plus T of V is the first condition. And in the second, say T of CU must equal to C T of U. Either you use this or نایبش مارسید بهش شێوەیە کەوتیش پیشانی ئەوکە کە لێن ترانسفۆرمیشنە بەژمارە میکە چونکە تۆ بەژمارە کە بۆ نمونەیە ڕاستە لای بۆ نمونەیەکی ڕاست وانە بان تۆ جێنەرەڵی کە پروڤی کرد کەشین. Okay, either use this or use T of CU plus V must equal to C T of U plus T of V. Okay, here in this example, this is used, and also you can use this to show that if it satisfies this condition, means it's a linear transformation. If not, it's not. Okay, look here we let A and B belongs to M by N. Look, we pick vectors here. We must get the result here. Okay, we took A and B as two vectors, so the sum of the sum of them is the transpose of their sum. And in the transpose of matrices, we say if we have the sum of two matrices and then raise to the transpose, you can give the transpose for each. So it's A of T plus B of T. What's A of T? Can I say it's T of A or not? It's the image of A. Because here, T of A is A of T. How about T of B? BT. Okay, it's BT. AT plus BT is T of A plus T of B. So we show that T of AB is T of A plus B is T of A plus T of B. It's the first condition. It's satisfied. The second one, T of CA is equal to CA transpose. And we can bring this to out. And we get CA transpose. So A transpose is T of A. That means it equals to CT of A. It satisfies the second conditions. You can also use this condition. You can also use this. Let's use this one. Here, T of CA plus B. We don't use U and V. U and V are also vectors, but at the beginning we said we use capital letters for matrices. Okay? This equals to CA plus B all transpose. We can give the transpose for both. It is CA transpose plus B transpose. What's A transpose? T of A plus this is T of B. Look, we satisfied. That's enough. So we show that's a linear transformation. Do you have any question about that? Okay, we have only this example. We finished this and it's enough for today. We let T to be a function from R cubed to R2. Be a linear transformation. It says it's a linear transformation. Okay? T is a linear transformation. That means it satisfies all conditions of the linear transformation. And let B be the standard basis for R3. Look, what are the standard basis of R3? I think we talked about this. In R2, the standard basis of R2 are these two bases. It's 1, 0, 0. This for R2. These are it's E1, E2. And these two together are called the standard basis for R2. You should know this. It's trivial. So what are the standard basis of R3? Of R3. How about R3? We say it's 3 vectors. E1 equals 1, 0, 0. Okay. E2 equals 0, 1, 0. E3 equals 0, 0, 1. Yeah. And you can pick this for E1. This is for E3. This is for E2. Okay. التواني هالكامل كان بإي1 داني كيشني بس مهم أمس يعني هذا الشيء إتر كاميان إي1 كاميان إي2 كاميان إي3 كيشنيه شيء أما standard base كوتي standard base أمي how about for R4 بله أو كذا يبقى شوالي أي بوماتريكس كي do by do if you have for M 2 by 2 what's the standard base of M2 by 2 سيركي ليرة شوال ماتريكس مان هي شو كدو باي 2 أبي شوال ماتريكس مان كاتني R3 أبي سين مان R2 2 إما بو ماتريكس دايمنشن كيدو سينو دو كرا دو شوال تعتبر شوال بيس مان ونيا يك دو سي شوال E1 ببرن يك 0 0 0 0 يك 0 0 0 0 يك 0 أما بريتلا ستاندرد بيس بو ماتريكس كي بادو اي بو سي باي سي نو دانا بدو كان بوشيوي باشا ما ستاندرد بيس كان يساوي بيسان او look here let D be the standard base of R3 so these are the elements of the standard base it says if T of E1 equals this. So T of E1, we don't know which one is E1, okay? And T of E2 is this. T of E3 is this. These are the image of T of E1. The image of E1, E2, E3, okay? It says find T of V, where V to be this. We need to find the image of this vector. we need to find the image of this vector. Look, we say since we have this, B is the standard base, since B is the standard base, so any vector could be written as the linear combination of the bases. We studied this before. Okay, we say any vector in the vector space should be written in this linear combination of the bases. And here you have the bases. It says they are the standard bases. Okay, so we need to write down this vector in the linear combination of E1, E2, E3. These are E1, E2, E3. We say this C1, E1 plus C2, E2 plus C3, E3. That's it. Okay, and here we get only one vector. It's one. So it's C1, C2, C3. We get that. What's C1? What's C2? What's C3? 2. So these are C1, C2, and C3. Now we say T of V is T of the sum of these three. Since we say V is equal to C1 E1 plus C2 E2 plus C3 E3. That means the image of this is equal to the image of this. These are equal. We need to just find the image of this summation, which will be the image of V. Here we say it is T of E1 plus 3E2 plus 3E3. This equals to T of E1 plus 3, because it's a scalar, we can take it out, okay? Plus 2, T of E3. What are T of E1, T of E2, and T of E3? They are given. This T of E1, it's 1, 1. T of E2 is -1 and 2. T of E3 is 0 and 1. We just substitute these three, T of E1, T of E2, and T of E3 here. And we get this, which is 2 and -2 and 9. That means T of V is -2 and 9. Here, the idea of this example is that to know the standard basis, and you should write down the vector in the linear combination of the standard basis. After doing this, you just need to find the image of the linear combination of the standard basis, which will be the image of the given vector. And that's it. That's enough for today. On next Monday, we will continue to finish this chapter, and we start next chapter also.